Hi folks, welcome to this lesson on definite integrals and applications in kinematics. So to start with, we're going to look at a kinematics question or a motion question from stuff that we've already done through differentiation. So here is the position function. Time is in seconds, it's from 0 to 5. We want to find the velocity function. So velocity function is just the derivative of the position function. So that would be 2t minus 6. Great. Find the intervals when it's moving right and moving left. So to figure that out, we need to know when is velocity 0. Velocity is equal to 0. Because that's when it might change directions. So I can set velocity, which is 2t minus 6, to equal 0. Or I can just, by inspection, say, oh, I know that it's just going to be 3. Right? T equals 3, sometimes we call that a critical value on velocity. So if I were to think about velocity over the time interval, really we only care about times from 0 to 5 here, because this is only defined in that segment. So velocity, if I plugged in a number between 0 and 3 into this velocity function, I guarantee you it would give me a negative value, which means that position would be decreasing, or would be traveling leftward. If I put in a number between 3 and 5 into this velocity function, well, it'll give me a positive value, which means that we're traveling to the right. So moving left, that's from 0 to 3. Moving right is from 3 to 5. Exactly whether you include 3 or 5 or 0 is not really that big a deal. But definitely over those intervals, we're moving left and right respectively. So in part C, we're asked to draw the motion diagram. And so to answer that, we've got to figure out, where did the particle start? Where was it when it changed directions? And where did it end? Because the interval's only from 0 to 5 here. So s at 0, if I put 0 into this, I'm going to get 0 squared minus 6 times 0 plus 5. So when this particle starts its motion, here's the origin. What are we in? We're in meters, 0 meters. And it starts its motion right here at 5. When time equals 0, that's where it is. When s is 3, let's figure out where it is. So I'd end up with 9 minus 6 times 3 plus 5. That would give me negative 4. So at 3 seconds old, it's going to be back here at negative 4. So it would have traveled to the left. That's no surprise. It went here. I'm showing it kind of go up a little bit, but really it's just moving left and right. At t equals 3, that's where it is. Okay. And then finally, where does it end up? Okay, when s is 5, we'd have, let's see, 25 minus 6 times 5 plus 5. We'd have 0. So it would go back towards the origin at t equals 5. Does this make sense with our velocity diagram here? Yeah, it moved left, then it moved right. So notice in the motion diagram, the x-axis is position. In the velocity sort of sign diagram, the axis that we're using, or the way we're chunking it up, is with time. Now here are the questions we want to answer. What's the displacement? The displacement just means, how do the starting and ending positions compare to each other? The ending position is 5 meters left of where it started. So displacement should be negative 5. One way that we can find displacement is just the change in s, meaning s final minus s initial. And final position minus initial position. So that would be 0 minus 5 or negative 5. That is displacement over those 5 seconds. What it tells us is that it ended up 5 meters left of where it started. That's what the negative displacement means, is that it's left of where it started. Now, the other question is the total distance traveled. That essentially means how long a path did it take? Well, it went this way, which is 9 meters. So total distance is going to be 9 meters plus another 4 meters. Distance can't be negative. Displacement and position can be negative, but distance is always going to be positive. So that's one way that we can answer these questions. We can come up with a motion diagram and figure out the total distance. We could have done the displacement pretty easily, but maybe there are slicker ways to approach this. Let's recall that speed is the absolute value, or the magnitude of velocity. And here are two properties that we can now exploit now that we know a bit about integral calculus. The definite integral of velocity gives us the net displacement. So net displacement right here is the integral of velocity from a starting time to an ending time. The definite integral of speed gives us the total distance traveled. So total distance traveled equals the integral of, oh, this means speed right here, the absolute value of velocity. So now we can redo question D using these integral definitions. We knew that v of t was 2t minus 6. So if I want the net displacement, I can find it by doing the integral of velocity from 0 to 5. So for us, that's 2t minus 6. And I'm just going to do this with the GDC. I press Math. I go down to my definite integral. One more. There we go. This pops up. I have 0 to 5. And I'm going to use x as my variable, 2x minus 6. And I'll just hit enter. Gives me negative 5, just like we got by doing it analytically. That's not a whole lot harder or easier than doing it just using the position function, especially since you had the position function. The total distance traveled, however, that will be a big win. So it will be from 0 to 5 of the absolute value of velocity, so the absolute value of 2t minus 6. That integral is kind of hard to do analytically, but it's not that difficult to do with our GDC. So again, I hit Math, I go down, and I find the definite integral. I'm going from 0 to 5. And now I press Math again, and I go over 1 to the right to number. And right at the top, it has absolute values. So I've hit Enter to choose that. And now I'll put in my function, 2x minus 6. And it very quickly finds that total distance traveled. We don't need one of those motion diagrams. So even if you have the position function, it's often easier just to find the velocity function and use an integral to find either net displacement or distance traveled. So the question we might ask at this point is, okay, well, how are we going to do this in a question that might not have access to your GDC? And one common way is to present a graph. So if we want the displacement over 11 seconds, where this is the velocity graph that's shown right here, the displacement is going to be the integral of that function, of that velocity graph from 0 to 11. And to find that integral, we can just count the blocks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then these two together make 14, and then this whole thing is half of a 4 by 1 rectangle, so this is 16 right here. That's the area that we're dealing with. This one here, I mean, the area is 1/2 base, which would be 3, times height, so that'll give us 6 here as an area. And this one here, again, this is a triangle, so it's 1/2 base, which would be 3 here, times a height of 2. This will be 3. When we evaluate that integral. The 16 is counted positively. The 6 is counted negatively because it's below the x-axis. And the 3 is counted positively. So that's 19 minus 6. The net displacement is going to be 13 meters. Okay, coincidence that it's the same number as the last one. But that just means that we end up 13 meters forward or to the right or above where we started. If we want to find total distance traveled, let's choose a different color. That would be the integral of the absolute value of velocity. Now, if you want to, you can just say, okay, well, that means all the areas are going to be positive. That's just going to be 16 plus 6 plus 3. We'll get 25. If that doesn't sit very well with you, what an absolute value does is it bumps things above the x-axis. So this section here that was problematic, it's going to get bumped up on the absolute value function so that it looks like this. So what I'm going to trace in purple is the speed graph, because speed can never be negative. And we can see by just looking at these numbers, we add them up, we're going to get 25. So even though it ended up 13 meters right of where it started, it traveled a total of 25 meters because some of that motion was backwards. There's some practice in your book on page 571, numbers 1 to 6. I hope this has been helpful. Good luck with the material, folks, and take care.